This is BlueEngineering, presenting on the Integrated Vision Inspection System, also known as IVIS. The team comprises of myself, Yu Heng, and my 3 team members, Zicheng, Junheng, and Sky. All of us are from Year 2 Electrical and Electronics Engineering. Now, there are 2 main challenges that still plague the construction industry today, namely at the stages of pre-installation as well as mid-installation or pre-handover. Pre-installation specifically regarding ineffective reporting of defects during material receiving inspections, and because of this, the overproduction of materials to act as spare parts, of course, may not be used. So that is the first challenge. And the second one being during pre-handover, the inefficiencies of work inspection requests, specifically ones that require manual labor, is prone to human error and generally ineffective, both of which will drastically increase the industry's carbon output and carbon footprint. Therefore, we are proposing to develop an accurate defection detection system that allows for just-in-time delivery processes by automatic interfacing between the site teams as well as the teams at the IVIS factory, as well as the automatic reporting system via defect reports that are directly generated and integrated into beam models as well as the IFC layout drawings as well. What we are proposing is to create a defect detection system that is AI-powered for accuracy, IoT integrated for ease, wearable for convenience, as well as automatic with minimal human interfacing.
The implementation of IVIS has significantly potential impact in Malaysia. Currently, construction waste can reach up to 54.6 tons per 100 square meters. But we believe with our IVIS systems, this can reduce drastically to around 1 to 1.5 tons or even eliminated. In terms of energy and emissions, studies show that up to 20% of energy wastage can be avoided, along with a 41.4% reduction in carbon dioxide emissions. This translates to approximate 48 gigawatts hours of energy savings and about 10k of tons of carbon dioxide avoidance per year. Furthermore, Malaysia is expected to require 1.3 million additional skilled workers in the TVET sector. The introduction of EVs support this by creating opportunity for high-skilled jobs in digital and smart construction technologies. Therefore, we believe that EVs not only contribute to the environmental sustainability, but also to the economic growth, workforce development as well.
In terms of the architectural design, the dual camera in ESP32 cam modules capture real-time stereo video images and transmitted it to a PC running a YOLO VX-based defect detection model trained specifically to identify construction defects. When the defect is identified, the system uses a GPS antenna to record the latitude and longitude of the inspection point. These coordinates are then processed through a transformation algorithm to convert GPS data into project grid coordinate, which is a local coordinate system designed specifically for a project site. Afterwards, all the collected data are stored in a cloud database and integrated directly into IFC drawings and BIM models to pinpoint the exact location for the workers to visualize exactly where is the issues. The system will then compile all this information to generate a comprehensive defect report. This is the YOLO VX-based training result. We trained our YOLO model based on 4 types of defects, which are holes, dents, corrosion, and cracks. On the left, the baseline training achieved an average precision of 0.5x3 with varying success across the different defects due to its size and complexity. And on the right, after applying data augmentation, hyperparameter tuning and freezing of initial training layers, and accounting for focal loss, the performance improved significantly, reaching a precision score of 0.x31. And you can see that the accuracy for each defect is all above 0.7. Here are some sample images of detection, where on left you can see that the confidence scores are lower at 0.4 to 0.6, while on the right the scores are significantly improved to 0.7 to 0.9.
From a financial perspective, IVIS is both feasible and cost-effective. Here will be cost breakdown of IVIS, which is around 2.8k for pilot implementation. Despite this initial investment, the system can generate saving around Rm 1,978 even at a small scale. Over the period of 3 years, the total net saving can reach approximately Rm 5,935. This demonstrates that IVIS not only improves efficiency but also provides a strong return on investment around 45.8%. Moving to SWOT analysis, it further highlights the strength and potential of our system. The strengths of our system include real-time defect detection with minimal human error, as well as improved efficiency and traceability of materials. However, there are also some limitations. Firstly, user adoption may be a challenge, as workers need time to adapt to new technologies. This can be addressed by providing a proper training and tutorials to help users become familiar with the system. Secondly, the device has limited battery life. To overcome this, we propose a battery exchange method where 2 sets of batteries are provided for each IVIS unit to ensure continuous operations. In terms of opportunity, we believe this is the right time to introduce IVIS into the market. Our technology aligns with sustainable goals, especially as Malaysia is moving toward achieving net zero emissions and adopting greener construction practices. Furthermore, the application of IVIS is not limited to the construction sector. It can also be extended to other industries, such as automotive manufacturing, drone-based inspection, and infrastructure monitoring. Due to its flexible design, the system can be integrated with platforms like drones, making it highly useful in hazardous environments, such as solar panel inspections or high-risk industrial areas. However, there are also potential threats. The main concerns involve data privacy, regulatory approvals, and compliance requirements. These challenges can be addressed by ensuring that the system meets relevant industry standards and regulation. In Malaysia, this includes compliance with the Malaysian Communication and Multimedia Commission for data communication and network usage. Additionally, the system should align with international standards such as ISO standards. For construction and BIM integration, compliance with ISO 19650 ensures proper handling of digital construction data. Furthermore, safety compliance with Department of Occupational Safety and Health guidelines is essential to ensure the device is safe for on-site use. By adhering to these standards and regulation, we can ensure that IVIS is not only innovative but also safe, reliable, and ready for real-world implementation.
From a sustainability perspective, IVIS support a cradle-to-grave approach in constructions. It enhances efficiency at every stage for manufacturing and also material inspections to on-site construction and finally inspections. By reducing rework and material waste, the system helps lower energy consumption and carbon emissions. This made IVIS a strong contribute to the sustainability construction practice. In addition, our solution also aligns several United Nations Sustainable Development Goals (SDGs). It directly supports SDG 9 by promoting industry innovations, SDG 11 by contributing to sustainability, and as well as SDG 12 by reducing the waste generations. Directly, it also supports SDG 7 by improving energy efficiency. This alignment highlights the broader global relevance of our solutions.
Inspectors, there's a surface defect. Please assess its severity if minor, initiate immediate repair, if critical, escalate to the engineering team for further evaluation. Ensure the defect is addressed appropriately before proceeding.